It'd been nice to have some people there, but it's not going to happen. Here's Felix.
Well, red baby dress.
All right, good evening.
Red baby dress.
Glad everybody could make it tonight. For those who don't know me, I'm Felix Meyer. I'm the Emergency Management Director for the county. We have 3 speakers tonight. Dr. Stephen Marsack from the University of Illinois. He'll be first. And Larry Pierce from the Missouri Department of Missouri Geological Survey. And then Steve Bessner from the State Emergency Management. Before we get started, I'd like to thank St. Genevieve R2 School District for putting this on and for Steve for organizing it. So if you have any questions, you can ask them right after the speaker, or you can hold them until the end, and we'll try to cover them for you. So, don't be afraid to ask questions. That's what we're here for tonight. So, Dr. Mansack?
Well, good evening. Does this sound okay or a little too loud?
Good.
Okay. So I want to basically give you an introduction to what earthquakes are, what happens during an earthquake, how people might be able to get some sense about how often they happen, and about understanding a little bit about why they occur. So I'm going to be dividing my presentation tonight into a number of different parts. I'm going to start by talking about what causes earthquakes. I'm going to then jump to the question of how geologists and how other people measure earthquakes and decide what's a big earthquake, what's a little earthquake. Then I'm going to focus in on a discussion of where earthquakes occur and why they occur where they do. And we'll see that the area that we're in here is somewhat unusual on a global basis as to the fact that there are earthquakes here. Most earthquakes happen in other kinds of places, but we'll have a better sense of that. Specifically, where we are right now is a region that's called an intraplate region. And you'll see what that means later. It's an area that's away from where most of the major faults on the planet are, so it's a little bit unusual that we have earthquakes here, but they occur. And then finally, I'm going to talk about an ongoing effort that's taking place right now. It's a project called EarthScope, and there's a local aspect of it that's called OINC. Now, you might wonder why OINC. It stands for Ozark, Illinois, Indiana, Kentucky, because it's an experiment that covers these 4 states, or this area. And I'll explain a little bit about what the initial results of that work are. So, to start with, let's talk a little bit about what causes earthquakes. So, in general, throughout the entire planet, most earthquakes are a consequence of slip on a fault or on the formation, or caused by the formation of a fault. Now, what is a fault? A fault is basically a fracture on which there's been sliding. So if you look at this exposure of an outcrop, an exposure of rock, you can see that there are a number of black horizons that are distinctive beds coming across the outcrop, but they're not continuous. They stop at lines that cut diagonally across the outcrop. So what we're seeing here is an example of a fault. It's a fracture on which there's been sliding, and the arrows indicate the sense of motion. These red lines represent layers that were originally continuous, but have been offset as a consequence of the displacement. Now, this is a fairly small fault, but when this did break sometime in the past, there would have been an earthquake in this area. Now, the reason that happens is that if you look at the way in which rock deforms, and the way in which the crust of the earth breaks in responses to the pushes or the pulls, or what geologists refer to as stresses, you see that what happens is there will be a period of time where the pushes and pulls, the stress, builds up in rock, and it begins to bend. Just like you start bending a stick. But just like when you bend a stick, it can only bend so far until it breaks. There's a limit to how much you can bend the outer layers of rock on the surface of the earth. And eventually they break, and when that happens, a new fault forms. That process is going to generate vibrations that pass through the earth, and those vibrations, when they reach the surface, cause an earthquake. Now, formation of a new fault, or formation of a new rupture in the earth is not the only way that earthquakes form. A lot of times, in fact, most times, there are pre-existing fractures, pre-existing breaks in the crust, which already exist, but are being held together by friction. But once again, you can build up stress until finally the little anchors on opposite sides of the fault that are holding it together break and the fault slips. That's called reactivation of a fault, or slip on a pre-existing fault. Now, you can look at that as an analogy to what happens if the wind blows on a sailing ship and the anchor holds it in place, but then suddenly the wind is strong enough that it causes the anchor cable to break. And when that happens, there's a separation and a motion. In rock, if that horizontal surface there with the roughnesses on it represents the plane of a fault, one of these fractures on which sliding occurs, and then it suddenly slips, again, rock breaks. And it's that breaking of rock that generates the energy of an earthquake. So what do faults look like? Well, most of the faults on the planet are deep down beneath the surface. We can't really see them at the surface, except in places where during mountain building processes, the overlying rocks have been stripped away, and we actually can see what was once underground. So here's an example of a fault that's exposed in an outcrop in the Colorado Rockies. Again, the way we recognize faults is by looking for some sort of marker, some sort of distinctive layer that suddenly gets offset. To emphasize that, I have a sketch here that shows this reddish marker bed suddenly offset to another level, and the boundary between those two is the fault. Again, when that thing moved, there was an earthquake. Here's a more familiar one. Everybody's probably heard of the San Andreas Fault in California. This one's very famous because it's very active, and also it intersects the ground surface while it's moving. So the trace, or the position where the fault intersects the ground surface, can be seen. And here we're looking at the fault obliquely from the air. We're sort of looking east. The trace of the fault is this trough that runs across the photograph right here. It formed because the fault breaks up rock, and so the rock is more easily carried away by rivers and by streams and by wind. So it ends up being a little depression because the rock is weaker. What's interesting here is you can see the course of a stream. It's a dry stream because this is a desert and it only flows during the rainy season. But it comes across here and then suddenly it's offset to this position here. That means that, let me go back to that slide. That's an example of the displacement on this fault. Probably not all during one event, in fact, definitely not all during one event, but accumulated over decades or centuries that's displaced that fault. And here again is a sketch to emphasize that displacement. The rock on this side, which is to the east, is moving to the right, and the rock closer towards us is moving towards the left. So what do faults look like? Well, in some cases, there's a distinct step at the surface of the Earth called a fault scarp, where the fault has offset the surface of the Earth. That's what we're seeing up here. This was a big fault scarp that formed during a 1958 earthquake in Nevada. It's probably about 12 feet high. In some cases, we actually see an exposure of the fault plane, and even in this, there's some lights on the stage here that are kind of obscuring this a little bit, but here you can see that there are scratches in the rock surface, and that's a consequence of one body of rock sliding against another, typical of what happens during a fault. And then finally here you can perhaps make out, here's a pen for scale, make out lots of little chunks and broken angular fragments. That's an example of the broken rock that develops when faults take place, or when faulting takes place. So geologists distinguish among different kinds of faults based on the direction in which the slip has taken place. So for example, if you imagine a person that's standing with their head above the fault and their feet below the fault, we can define the rock above the fault as the hanging wall, the rock below the fault as the footwall. If the hanging wall goes down, we call that a normal fault. If it goes up, we call that a reverse fault. If it goes sideways, it's called a strike-slip fault. You may see these terms in the news media every now and then. They're just terms that we use to describe the relative motion, the relative displacement across a fault as a consequence of slip. So, how do we have a sense of how much slip takes place? Well, first of all, when slip takes place on a big fault, it's probably not the entire length of the fault that's moving, but only a portion of it. So that's symbolically shown in this example here of a strike-slip fault, where the fault trace that had slip on it offset a series of fences, but then beyond the ends of the fault, the displacement dies out, and there's a place where the fences are just bent. In the case of the huge earthquake that happened in Japan in 2011, this was a particularly large area of faulting that slipped. The slip area is, as you can see from the scale here, probably about 600 or 700 kilometers across, or about 500 miles long. These red arrows are little GPS, are little arrows that measure the amount of motion as measured by a GPS. And what you can see is that Japan lurched to the east by as much as 12 meters or so, so 12 yards, during the slip on this earthquake. And then the displacement dies out to the north and south. And that's typical of the way a fault occurs, or fault behaves. When an earthquake happens, the earthquake happens in a certain portion of the fault, and then it dies out as you go away from that original location. Now, I mentioned briefly that earthquakes are basically vibrations. Same kind of vibrations that you get if you hit a rock with a hammer. It sends shock waves that you can feel if your hand's on the other side of the rock. This energy transmits or is transmitted through rock in the form of waves. And there are different kinds of waves. There are some kinds called body waves, which are waves that pass through the interior of the earth, pass through the body of the rock. And then there's another kind called surface waves, which are waves that cause the surface of the earth to undulate, go up and down or back and forth. Both of these can happen during an earthquake. And again, when we say that an earthquake has occurred, that means that the vibrations that happened in the place where a fault slipped have been transmitted to the surface of the earth and has caused the surface of the ground to shake. So this is sort of a more familiar example of what you might think of as an earthquake. Somewhere down at depth, it could be a few miles down, several miles down, in some cases even deeper. A fault breaks, and that fault generates vibrations that pass through the earth and eventually reach the surface of the earth, and it's where those vibrations reach the surface that the ground trembles. Now, there are different kinds of motions, depending on which waves are intersecting. Some waves go up and down, some waves go back and forth, some waves are snake-like, sinuous like so, some cause a rolling type motion. All of these are the different kinds of motions that can take place during an earthquake, which is why the vibration of an earthquake can be so chaotic. If you've ever seen, and you might be seeing some images of ground shaking during an earthquake, you get a sense that sometimes it's back and forth, sometimes up and down, sometimes all over the place. That's because there are all these different kinds of waves that are arriving, and each one has a shake in a different direction. Okay, so we've now introduced basically what an earthquake is, and probably most people have that fundamental idea already. What about measuring earthquakes? When we say that there's a big earthquake, or the news media has a headline that there's been a large earthquake in Japan, or there's been a small earthquake in Virginia, what does that mean? How do we measure and distinguish big earthquakes from little ones? Well, there are two scales. The first scale, the one that goes back longer, is called the Mercalli intensity scale. And you see this word intensity, often it's associated with a guy named Mercalli, who was the first one that came up with it. And basically, this is a scale that's based on what you feel and what damage you see in an area. So it's basically a subjective interpretation of the motion associated with an earthquake. And it's a scale that goes from 1 to 12, usually given with Roman numerals. A 1 is a vibration that's small enough that you barely feel it or don't feel it at all. Say a 5, unstable objects, chimneys and so forth may tip over. When you get down to 12, that's basically total devastation. Basically, all large buildings, unless they're particularly well built, are going to be turned to rubble. So the Mercalli intensity goes from barely anything up to intense total damage. Now, the important thing about the Mercalli scale, when you see numbers associated with this, is that the Mercalli scale varies with location. So for example, if you're right over where a big earthquake occurs, you may have Mercalli 10 to 12. But as you go further and further from the location of the earthquake, the intensity number goes down. So here's an example of a 1886 earthquake that occurred in Charleston, South Carolina. You can see that right at its center is a Mercalli intensity 10, and then by the time it got out to Illinois, it was Mercalli intensity 4. So it was actually felt in this part of the world. Here we are in St. Genevieve right there. It would have been felt, but barely enough to cause any damage. You can see that these lines or contours separate the zones in which the different intensity has been felt. Closer to this area, this is the Mercalli intensity map for the 1811 New Madrid earthquake. You can see red, the more intense earthquakes, 10 to 12, centered over the Boot Heel, centered over New Madrid, and then dying out progressively away from that. So that's what's meant by a Mercalli scale. The problem with using a Mercalli scale for, say, comparing an earthquake in, say, in Virginia to an earthquake in Japan and so forth, is that the amount of damage that's done, it's a subjective estimate. And if you're in an area where there aren't a lot of buildings, it might be hard to get a sense of what that damage is. So geologists, a number of years ago, decided that they were able to invent an instrument called a seismograph, or a seismometer, that actually measures the amplitude of the vibrations, meaning how much up and down motion or side-to-side motion actually takes place. The way it's done is there's a vault, usually these are anchored underground, in which this instrument is placed. And a seismometer basically consists of just a heavy weight connected to a frame And on that frame, in this old mechanical style seismometer, is a roll of paper. Now, because of Newton's law of motion, this weight just stays in place because it has inertia. And when the ground shakes, the frame and everything connected to the frame moves. And so this needle, which stays in place, will trace out the back and forth motion of the ground relative to that weight. So here's an example of installing a modern seismometer not too far from here in southernmost Illinois. Now they're electronic instruments. They have an electromagnet inside of them, a lot of fancy circuit boards and so forth, that basically does the same thing as that old style mechanical one. What it does is it records the amount of ground motion that takes place during an earthquake. Now with that, well, one last image. So let's say that you have earthquake waves that are coming from below. Before the earthquake, the needle traces out a straight line. When the earth goes down, the needle goes up. When the earth goes up, the needle goes down. So you end up with this kind of a record. Before an earthquake, the first earthquake wave to hit, a few more little vibrations, the second big earthquake to hit, vibration to hit, then the large ones come in usually a little bit later. You might wonder, well, why is it that these waves take so long to arrive at a recording station or at a seismometer? Well, it has to do with the fact that different waves travel at different velocities through the Earth. So this earliest one is called the P wave, stands for primary. The second one is called the S wave, the secondary wave. And then these are the surface waves. The different waves travel at different velocities, so they arrive at a recording station at different times. And here is an example of the record over a several-hour period. And you can see little vibrations that would be due to the noise of traffic, due to the noise of trees vibrating and so forth. And then a real earthquake comes in and you see a bit bigger vibration taking place. So this is what the record of a seismometer looks like. Now, the advantage of having records like this of earthquakes, and many advantages, you can say a lot about the nature of the waves, but another thing is that you're able to compare subjectively an earthquake that happens at one location to an earthquake that happens at another. There are various scales for doing this. The one that's probably the most familiar is called the Richter scale. It's actually not the one that's used anymore. There's another scale called the moment magnitude scale, which is really the record of, the accurate record of what an earthquake is these days. But the Richter scale is easier to understand. Basically, what Richter did back in the 30s was realize that you could measure the amplitude, that's the size, of the largest wave to be recorded at a location. And then what he did was sort of added or subtracted to make it seem like the seismometer that made this record was at exactly 100 kilometers from where the earthquake was. And so by doing that, he was able to say, okay, a large earthquake is going to cause larger amplitude motions at a distance of 100 kilometers, a smaller one will cause smaller amplitude motions. We can compare them to each other, and he came up with a number that's called a magnitude. So when you read about earthquake magnitude, it's not a measure of the amount of damage, though they're often correlated. It's a measure of the size of the waves that passed through the area, as if that area were 100 kilometers from the earthquake. So we now understand a little bit about what causes earthquakes: breaking of rocks, slipping on faults. Measuring earthquakes, we see that we can describe differences among earthquakes based on either the intensity, the amount of ground shaking is observed, or the magnitude, which is a measure of the size of the waves. Now let's look at where earthquakes occur, because they don't occur everywhere, and they occur in some places very, very frequently. So first of all, when we talk about the location of the earthquake, what are we talking about? Well, let's imagine an idealized example where we have a fault, the surface on which sliding occurs, that penetrates down deep into the earth. The place on the fault where the slip takes place, or where the rupture takes place, is called the focus. When you see a map that shows locations of earthquakes, obviously it can't show the focus because that's underground. So what it shows is a location called an epicenter. And the epicenter is simply the point on the ground surface directly above where the focus occurs. These you can plot on a map. So if you do that on a global basis and represent each earthquake by a red dot, that red dot represents the epicenter of the earthquake, you see that earthquakes don't occur evenly across the entire planet. It's not like a shotgun that spreads earthquakes everywhere. Rather, they occur in very distinct belts. Here's a belt along Alaska, along Japan, along South America, along Central America, Mexico, along western United States, across northern India, and some that are less well known because we rarely feel the consequence of these belts that run right down the middle of the ocean floor. This is called the East Pacific Rise. This is called the Mid-Atlantic Ridge. Now, the reason that these belts exist mystified geologists for a long time, but then in the 1960s, an idea came along that began to make sense of this. And what people now realize is that those belts of seismicity define what we now refer to as tectonic plates, or as just plates. So for example, you might remember the belt that I emphasized going around the Pacific Ocean floor and along the western United States, along Alaska. They outline a large region of the surface of the Earth called the Pacific Plate. Here's the Pacific Plate, the North American Plate, the South American Plate. Most of these have names that sound familiar, some don't. This is the Cocos Plate, the Nazca Plate, Australian Plate. There are about 8 to 10 large plates and about another 15 or 20 small ones on the surface of the Earth. In other words, the outer rigid shell of the surface of the Earth is broken into separate pieces called plates. And what causes earthquakes is that these pieces move relative to one another. And where they grind and crush against each other at their edges, at the so-called plate boundaries, is the place where most earthquakes occur. And that idea is called the theory of plate tectonics. Again, the outer layer of the Earth, which technically is called the lithosphere, is broken into pieces or plates, and these move relative to one another, and it's that motion that causes earthquakes in general. There are some other causes, but that's the dominant cause. Now, I mentioned that earthquakes happen at plate boundaries. Well, there are 3 kinds of plate boundaries defined by the nature of the motion. So on the one in the upper left, plates are moving apart. Geologists call that divergent motion. In the one in the middle here, plates are moving together. That's called convergent motion. Now, it turns out that you can't just have plates that come together and butt against each other like that. The way it works is that one plate descends and sinks back into the interior of the Earth beneath another. And that's what's symbolized here, where this purple layer, which represents the plate, has bent and is descending back down into the Earth's interior. So we have divergent plate boundaries, convergent plate boundaries. The last one is called transform plate boundary, and those are places where one plate is sliding sideways past the other one. That's actually the San Andreas Fault is an example of this one. So most earthquakes happen at those 3 plate boundaries. In fact, if I just go back quickly, this is a convergent plate boundary. All the ones along the western Pacific are convergent plate boundaries because the Pacific Ocean floor is sinking back into the Earth underneath Asia. Western South America is a convergent plate boundary. The Pacific Ocean floor is sinking underneath South America. Western North America is a transform boundary. And then these mid-ocean ridges that are out in the middle of the ocean floor, those are the divergent boundaries because that is where a process called seafloor spreading is taking place, where new ocean floor forms and gradually moves away, and as the consequence, the continents that are on either side drift apart. Now this process, I should say, happens very, very slowly in a human time scale. For example, on the Mid-Atlantic Ridge here, the motion is about 3 centimeters a year, about an inch or so a year, about the same rate that your fingernails grow. And so we can't see it with our naked eyes, of course, but actually modern GPS instruments can detect it. They have an accuracy down to 1 millimeter a year, and so it's very easy for GPS motions or devices, not the car kind, but the kind that are used for scientific research, to detect the motion of North America as it moves away from Africa. So in cross-section, what we see is a complicated planet with divergent boundaries, convergent boundaries, and transform boundaries. And that's the way the outer limit of the Earth works. But that's not where all earthquakes happen. There are several other places as well. If I draw a block representing the outer layer of the Earth, here's a transform boundary, but there are also places where the continental crust is beginning to stretch. It hasn't yet formed a new ocean basin, it may never, but it's beginning to pull apart. For example, in Nevada and Utah, this is happening now. And where that happens, a lot of faults develop in the crust, and so these areas, so-called rifts, are places where earthquakes occur. Similarly, where 2 continents crush together, continents, it's hard to believe, but continental crust is relatively buoyant. It's like a float. It can't sink back down into the interior of the Earth. So when two continents bash against each other, they form a mountain belt like the Himalayas to form, and that will also be a place where earthquakes occur. So rift zones and continental collision zones. To show you an example, currently there's a big rift running through East Africa, East African rift, a lot of earthquakes along it. Currently there's a collision zone between India and Asia, a lot of earthquakes along it. So those are examples of those. But in addition, there is another kind of earthquake, and that's bringing us closer to where we are right here, so-called intraplate earthquakes. Intraplate means within a plate. That means away from the plate boundaries, away from rifts, away from collision zones, places that you wouldn't normally expect earthquakes to occur because plates should be relatively strong inside. But they do occur. So let's look closer to home. Here's a Google Earth image. Here's Illinois for reference. The North American plate, the eastern edge is not actually the coast of North America. It's way out in the middle of the Atlantic Ocean. It's called the Mid-Atlantic Ridge, a divergent boundary. The southern boundary is along the Caribbean. The western boundary runs up through California. In California, it's a transform boundary. In Washington and Oregon, it's a convergent boundary, and that's why there are volcanoes here. But you'll see that where we are here is far away from any of those locations, so we're not in the plate boundary area. But if we look at this map of seismicity that was compiled by the U.S. Geological Survey, you can see by these red dots, which represent the epicenters, the locations of the earthquakes, that they occur all throughout this area. Now, one thing that's a little different about this map than the one I showed earlier, the size of the red dots here is in proportion to the magnitude of the earthquake. So bigger dots represent bigger magnitude of earthquakes, smaller dots represent smaller magnitude of earthquakes. And you can see, of course, that the New Madrid area, and then coming up through here, not far from St. Genevieve, there are a number of dots, so there are a number of earthquakes. So everyone's probably familiar with the famous New Madrid ones from 1811 and 1812, this artistic rendering of what might have happened during those events. But let's focus in instead on the geology of this area and try to understand what might be behind the earthquakes that occur in our part of the world. So here's a geologic map of North America. This map is designed so that the different colors represent different ages of rock. So the oranges and reds are the oldest rock. This is Precambrian age rock. The blues and purples are Paleozoic. The yellows and greens are Cenozoic. These are different intervals of geologic time. Red oldest, then purple and blue, and then yellow and green. Now, even if you don't know the colors or recognize these different ages, it is still clear from this map that there's a fundamental difference between the interior part of the continent and the edges of the continent. Just by looking at the pattern of the colors. Here we have big patches of the same color over broad areas. Oops. Whereas out here on the coast, we have lots of little broken up pieces, lots of things that are aligned in long ribbons. That's because on the east coast and the west coast, we have relatively recent mountain belts. The Appalachians on the east, the North American Cordillera, including the Rocky Mountains on the west. But the interior part of the continent is a region that geologists refer to as a craton. Craton is a word that refers to the old, stable, long-lasting part of the continent. And in the case of North America, there are two parts of the craton. There's the part where the oldest rocks are exposed, the Precambrian rocks we call them, are exposed in an area called the Canadian Shield, and then an area called the Cratonic Platform, where these old rocks are covered by younger sedimentary rocks, Paleozoic and Mesozoic sedimentary rocks. Now, if you've driven from here west, you may know that along the highway you see layer upon layer upon layer of limestone. Those are an example of the younger sedimentary rocks. But if you go into the St. Francis Mountains, you can see the old granites and volcanic rocks. Those are some examples of Precambrian rocks that have been uplifted. This is a particularly unusual part of the craton because this is one of the few places where the oldest rocks peek through this cover of younger sediments. Excuse me. So if we look more closely at the layers of sedimentary rocks, like the limestones out on the highway here in our part of the world, we see that the ages define bullseye patterns. There are places where the surface of the earth worked down as these layers were being deposited, creating a bowl-like depression, and that's called a basin. And then places where the surface of the earth worked up or was remaining high over long periods of geologic time, so the sediments are thinner, and those are called domes or arches. So for example, here we have the Illinois Basin, which is an area where the sediments are warped down and are thicker. And just to the west of us, the Ozark Dome, where the basement, the old Precambrian rock, is up higher and the sedimentary layers are much thinner. So right from the start here, we see that we're actually in a fairly unusual region. St. Genevieve Fault is running right through this area here. We're at the boundary between two fundamentally different pieces of North American craton, the dome and the basin. Let's look at a more detailed geologic map. Again, the details aren't that important, but the colors represent different ages of rock. You can see the Illinois Basin here, and you can see the Ozark Dome here. And here's the Mississippi River running right along the boundary between these two geologic provinces. There's a reason the Mississippi is flowing there. It's not just random. It's basically abutted against this Ozark Dome or this Ozark Plateau. Now, if we look at the topography of this area, and again, the lighting on the screen is a little washed out, but on this map, the browner colors represent higher areas, and the bluer colors or greener colors represent lower areas. Again, we can see that this reach of the Mississippi River forms the boundary between higher lands, or the Ozark Plateau, and the lower lands of the Illinois Basin. There's a detail of that. Again, high is brown, low is bluish-green. Here's the Mississippi embayment down here, the Boot Heel, and then we have the St. Genevieve section coming right through here. So again, we see geologically, this is an important boundary. Topographically, it's an important boundary. There's something going on here. And that's the trace of, roughly speaking, a structure called the St. Genevieve Fault, which is a recognized fault in this part of the world. Well, one way to get a handle on what's going on here is to strip away all of the sedimentary layers, all the limestones and the other layers beneath, and look at what the shape of the underlying so-called basement is, the granites that are underneath that. This map, if you're used to looking at these maps, it will stand out for you, but if you're not, let me guide you a little bit. Basically, these lines are contour lines. So this is like a topographic map that shows the shape of the land surface. Only these lines are not on the land surface. They are on the boundary between the sedimentary rocks, the limestones and sandstones and so forth, and the granite below. The key thing is that we've also shaded this map to give you a sort of three-dimensional perspective of low areas and high areas. And what you can see is that where it's very, very low, that's the Illinois Basin. Where it's very high, it's the Ozark Plateau. And the boundary is the St. Genevieve region along here. Now, if we take that map and turn it on its side, and exaggerate it a little bit, because everything's fairly flat here, so you have to exaggerate by 40 times to make it stand out. Here's the border of Illinois, here's the Ozark Plateau, here's the Illinois Basin, and here's the reach of the Mississippi that's just to the east of us right here. I guess we're located right about there. And you can see, once again, that this is actually a pretty important boundary between an area that's fairly high and an area that's fairly low. In fact, there's 7.5 kilometers between the rocks that, well, let me restate that. If you were to go to stand on the Ozark granite in the St. Francis Mountains, and then go less than 100 miles to the east, that same rock would be 7.5 kilometers below the surface. That's a lot of difference. That's a lot of distance. And that's called the structural relief. Here's a cross-section. This is like a vertical slice through that area to emphasize it again. Here, the orange line represents the boundary between the old granites and the younger sedimentary rocks. These other colors are the sedimentary rocks. We go from the Ozark Plateau and drop down 7.5 kilometers into the Illinois Basin. And the St. Genevieve Fault is symbolically shown by one of these lines here. Now that gives you a sense of that, 7.5 kilometers. I'm sorry, I'm used to speaking in metric, so that'd be about 5 miles or so. Go out to the front range of Colorado. Here's Colorado Springs, Pikes Peak. That's 1.7 kilometers up there. So we're looking at about 4 or 5 times that distance of structural relief beneath us, just in this area right here. We just don't see it because instead of being exposed like this mountain range here, imagine that this was completely filled up with sediment, so we just don't see that distance there, but it's beneath us. So in the mountain ranges, you see it. In our part of the world, you don't, but it's still there. To emphasize that again, let's look at this so-called structural relief on the scale of the entire continent. Again, it's a little bit hard to see with the lighting of this projection, but basically the darker colors are where there are deep basins, and the lighter colors are where they're not. And here you can see basins all along the edge of the craton. Here's the Illinois Basin right here in the boundary in the plateau. So you can get a sense of what I'm driving at is that the reason that there are earthquakes in this part of the world is because there are some faults here. And these faults probably are very, very long-lived faults, but once formed have remained fairly weak. So the pushes and pulls that act on the continent, the stresses, are enough to cause them to slip every now and then, even though we're not on a plate boundary. These red lines represent the traces of various faults that have been reported throughout the continental interior. Not all of these are active. These are not all like the San Andreas Fault, in the sense that they've got lots of slip on them every year. But they are places that did have some slip on them on the past, and in a few cases are weak enough so that there could be some slip on them in the future. And here's the St. Genevieve right there. Focusing in, once again, here's the St. Genevieve Fault, right along the, sort of just crossing the Illinois-Missouri border. A little bit closer detail. There's a whole series of faults that sort of are crisscrossing in here, making you wonder whether this is a particularly weak area because there are so many faults in this part of the world. And you get that impression by looking at a map showing the distribution of epicenters. The little yellow dots are epicenters, and you can see that they come up through the Mississippi Embayment, and then there's a strand of them that extends up along the Mississippi River. Here again, the bulk of them are down in the New Madrid area, but here's the St. Genevieve area, and you can see this belt of earthquakes that extends up through into central Missouri. Now, what does that mean in terms of earthquake risk? Well, that's a much harder question to answer. And different people come up with different interpretations. A map that came out several years ago by the USGS used colors, these very dark colors, to give the impression that the hazard here is as intensive as it is in California. I don't know, there are a lot of geologists that would disagree with that and say instead that yes, there's a risk of earthquakes here. It's probably not as severe as it is out in California because big earthquakes happen much more frequently out there than they do here. But they do happen here, and so it is an area to be concerned about. Well, how do you characterize that concern? Well, one way, and you may have heard of this number, is called the recurrence interval. But the recurrence interval is often misinterpreted. The recurrence interval technically is the average time between earthquakes of a given size. So if you say that the recurrence interval is, say, 100 years, that doesn't mean that an earthquake happens every 100 years. It's not like, it's not periodic, it's not like clockwork. It's that on average, over thousands of years, they come out to happen about once every 100 years. It could happen in 120 years, it could happen in 300 years, it could happen in 50 years. But it's on that order. Now, another way of looking at earthquake hazard is to define a number called the annual probability. And that's just simply 1 over the recurrence interval. So if you have a 100-year event, that means there's roughly a 1% chance of an event like that happening in a given year. And so sometimes people talk about recurrence intervals, sometimes people talk about annual probability. They're both ways of representing earthquake risk in the area. Where do the numbers come from? Well, first of all, one way of looking at it is to think in terms of how earthquakes work. And you may remember right at the beginning of the talk, I showed you how a block of crust would gradually bend and bend and bend and then suddenly snap. And that sudden snap is the earthquake. Well, that phenomena overall is called stick-slip. You can have a fault, it sticks for a while, stress builds on it, and then suddenly it slips. Sticks for a while, stress builds, suddenly it slips. Oops. So, looking at this, you can simulate that by imagining that you've got a brick sitting on a table connected to a spring. If you pull the spring, the brick still sits there because of friction. But then suddenly, there's enough pull that it suddenly slips. So the stress builds, and then suddenly it slips, and that's a faulting event. So there's a reason why earthquakes don't happen continuously. Faults have a certain strength to them due to friction, so the stress has to build up for a while until finally a slip event occurs. Now, how do you get at the recurrence interval for a region? Well, the clues come from looking at geology. Now, in the case of places where earthquakes happen all the time, there's a historic record, and you just look at the historic record. But in places like here, there aren't enough earthquakes happening over history to be able to come up with enough events to be able to characterize the recurrence interval. So geologists instead have to look at geologic evidence that's buried in the earth. And one trick is to go to an area where there's faulting and look at the layers of of sediments that are under the ground and look for cues such as, I'll show you an example in a minute, sand volcanoes, or broken up and displaced, broken little debris flows and things like that happen underground. And if you are lucky enough to be able to find some sort of datable piece of wood or vegetation using carbon-14 so that you can get an age of this, then you can determine the time at which these events happened in the past, even if they were thousands of years ago. So, again, what geologists will look at is they'll look at places where a sand volcano occurs and then later got buried by more sediments. This is a modern day sand volcano, obviously burying some crops. Basically what happened was there was a layer of liquefied sand below. When an earthquake happened, the ground cracked. The sand squeezed up and erupted at the surface and spread out over the surface. Here's an example in Missouri where you can see these white, it's not a very high resolution photograph, but these white patches on the fields are examples of sand blows that happened after an earthquake. So people study this by digging trenches and looking for features such as this sand channel and the relic of a sand volcano, and then determining their ages. And then from adding all that up, they're able to come up with a recurrence interval and give an estimate as to what the annual probability of an earthquake in a given area is. But the important thing to keep in mind is that there is no technology known, and many geologists think that there will never be a technology known that will allow you to pinpoint exactly when an earthquake is going to happen in the future. You can't say there's going to be an earthquake on such and such a day 3 years from now. It's just not possible because there's enough randomness to the process that it's really not predictable at that level. But you can say, for example, that it's more likely that an earthquake will happen, say, in Japan than in northern Canada, because Japan is on a seismic belt, northern Canada is not. So we've seen that the recurrence interval is based on studying paleoseismology. In the case of the San Andreas, more or less 150 to 200 years is a number that's thrown out as the recurrence interval. In this part of the world, it's much more debatable because the evidence is not as abundant, and I've seen estimates everywhere from 500 years to 3,000 years. So maybe the 1811, 1812 events might not happen again for centuries or millennia, or they could happen sometime soon. Hard to say. So I'll finish off now by talking about a new experiment that's underway to try to get a little bit more insight into the nature of the crust in this part of the world and the nature of the seismicity in this part of the world. It's a project that's funded under the overall name of EarthScope, which is a 10-year project funded by the National Science Foundation that has the purpose of setting up a very dense, or relatively dense array of seismometers in a band across the continent, closely enough spaced so that they can actually image what the nature of the structure inside the Earth is. In general, seismometers are hundreds to several hundred kilometers apart, but in the case of the EarthScope project, the seismometers are spaced at 70 kilometers apart, about 50 miles apart. And this project's been operating for 10 years. It started out in the West, and what happens is there's a team of technicians that is constantly working, picking up instruments off the backside and sticking them on the front side. And as a consequence, this whole belt, or this whole band of seismometers has been migrating across the country, sort of like a caterpillar tractor migrates across the country. It's passed through here now. It's actually reached the East Coast, and the instruments are being picked up and sent to Alaska so that they can do the same experiment in Alaska. This was where the array was in 2012, about 3 years ago or so, when it's traveled this part of the world. Now, to get even higher resolution, more detailed image of what's underground, it was possible for individual groups of geologists and seismologists to get together and make a proposal to the National Science Foundation and ask for additional funding to obtain even more instruments to so-called densify the array within a certain area. And a consortium of the University of Indiana University, Purdue University, University of Illinois, the Illinois State Geological Survey, and the Indiana Geological Survey got together and were successful in getting a project funded. And it's called OINC, it stands for Ozark, Illinois, Indiana, Kentucky. And it allowed us to put instruments at 10 kilometer spacing instead of 70 kilometer spacing, going from central Missouri across southern Illinois into central Kentucky. And this is basically the distribution of the array. And as you can see, again, the light's not good, but you can see it goes from the Ozark Plateau across that big boundary between the Ozark Plateau and the Illinois Basin, and across the Illinois Basin into Kentucky. The experiment's almost done now. The instruments are now being picked up and sent elsewhere. But this gives an example, lots and lots of instruments, lots and lots of records, and for reasons that are beyond the scope of this talk, it's possible to use this information to see inside the Earth and basically make an image of the inside the same way that a CAT scan makes an image inside a human body. But it also allows you to get much better resolution on small earthquakes that happen in our part of the world. So here's the trace of the St. Genevieve Fault. Comes across here. Focus in on that area. You may have looked at it in Google Earth. Here's the Mississippi River. The St. Genevieve structure is running across through here, looking along the length of it. It comes into Illinois a little bit. And I had a student a few years ago who made a map of this portion of it, the southeastern end of it. And here are the details. It seems like there are lots of smaller faults within the St. Genevieve Fault, just across the border in Illinois. The key thing about this is it emphasizes that these faults, based on the geological relationships across them, these were active a couple hundred million years ago, or a few hundred million years ago. So this emphasizes that the St. Genevieve structure is probably reactivation of a very, very long-lived fault, a weakness in the crust that extends back, had its origin perhaps in the Precambrian, has been reactivated throughout the last half billion years or so. Now, one possible explanation for that is that all these faults in the continental interior, all these faults in the craton, are actually a consequence of rifting, this process of stretching and breaking the crust that happened back during the Precambrian. These red bands represent places where there's a record of rifting, and these other lines represent faults that are probably related to those, but there isn't as much known about them to be able to define these red bands. So just like today, there's a rift in East Africa, and there's also a rift out in Nevada and Utah, where the crust is stretching. Back in the Precambrian, there was probably rifting happening in the central part of the United States, or it wasn't in the United States back then, but in the central part of the craton. And those faults, they stop moving, but they are still there as permanent scars that are weak enough to occasionally slip. And that's what's causing this unusual amount of intraplate seismicity in the mid-continent of the United States. A detail showing Illinois. Probably there are a lot of faults running up the axis of Illinois. Probably these represent the old boundaries of an old rift. This portion of it is fairly active. That's the Wabash Valley seismic zone. And here's the St. Genevieve structure. So, a basic model, again looking in cross-section, meaning a vertical slice through the Earth. There are probably these faults that penetrate down maybe 15, 20 kilometers or so. Up near the surface, they split into a number of splays, what geologists refer to as a flower, and they've offset layers of strata. They die out, up dip into bends. And you can actually see these bends. This is using oil well data to represent the surface of a layer of rock beneath the surface of the Earth and show how it's arched in 3D. So this is what it really looks like underground. So I'll finish off then by just focusing on some of the newer results from the OINC project. This is a compilation of earthquakes that were measured by the OINC instruments, and you can see the trace of the St. Genevieve Fault, and you can see there are a number of small bodies. These are all very small earthquakes, all under magnitude, mostly under magnitude 5, mostly under magnitude 3 or even 2. Very small. In many cases, people wouldn't actually even feel them, but they're strong enough to be detected by very sensitive seismometers. But it gives you a sense that there's a New Madrid system here, there's another belt of earthquakes coming across here, another belt running closer to the base of the Ozarks, and then the Wabash Valley zone that's coming up in Illinois. So I'll just, last two slides, just show some of the other work. Using that ability of this data to tell us about what the shape of the Earth is underground, one of the investigators, Hirsch Gilbert, who's at Purdue, has shown that the base of the crust, the outermost layer of the Earth, actually steps down about 7 kilometers, about 5 miles beneath the bound where we are right now. This is a very unusual finding. We didn't expect to see that at all. But basically, the base of the crust has a step in it of about 5 miles, just like the upper part has a step in it. So there's something going on here. And then these different colors represent different characters of the crust, or the layer below the crust. And again, you can see there's something strange. Here's the Mississippi River. This is a three-dimensional image. We're beginning to get a sense that there's some reason that the Illinois Basin and the Ozark Plateau are juxtaposed in this part of the world. So, in conclusion, I basically tried to give a brief introduction to what earthquakes are, how they occur, how they generate energy, why they occur where they do. Pointed out that the vast majority, like over 98% of earthquakes, happen along plate boundaries, but there are still a couple percent that happen elsewhere. And some of those are within plates, so-called intraplate earthquakes, which are probably following old faults that are still weak enough to slip every now and then. St. Genevieve might be one of these structures, and it's particularly interesting because it seems like it might be the surface manifestation of an important boundary between two different pieces of the North American crust. But there's still a lot to be studied to understand the nature of that boundary more. Based on the new results from the Oink experiment, it does seem that there's more earthquake activity on the St. Genevieve than people previously recognized, but again, these are all very small earthquakes. But it does mean that it's a fault that people should pay attention to. It's something that probably has been understudied so far and warrants a little bit further examination. But overall, any discussion that has to do with the likelihood of earthquakes happening, you always have to keep in mind that there's no technology that allows you to predict exactly when or where an earthquake is going to occur. And so it's good to be cautious, but it's not, there's nothing different now than there was 2 years ago before the Oink project that makes any different expectation about future earthquake activity happening on St. Genevieve. So I'll stop there and be happy to take a few questions. Yeah, back there. Well, I didn't use the word, but I showed it a little bit. Go back a few slides. So, liquefaction refers to the phenomenon where sand that is not stuck together, hasn't yet been cemented together, and has water in it, undergoes shaking. When that happens, the water pressure between the grains starts pushing the grains apart. And the mixture of sand and water, whereas before, when it was standing still and was able to support a load, becomes basically like a slurry. Mud, over the top of that, sometimes can be compacted more tightly and therefore is a little bit rigid. And when that happens, the mud can crack and can create a conduit through which the liquefied sand can reach the surface. What I didn't show here, but can also happen, is this layer the layers of overlying material can sink into the liquefied sand. And what that means is that if you have any buildings built on top of that material, and you have liquefaction with sand beneath, it can cause foundation collapse and it can cause damage to the buildings over the top. So liquefaction is something that happens when you have unconsolidated sedimentary strata, meaning that you've got layers of sediment that have not yet been stuck together by cement to form rock. And it is something that happens in this part of the world because of the nature of the sediments that have been deposited in the Mississippi Valley. Well, the question is, how pervasive would liquefaction be if there's a strong earthquake? It depends on how broad the area that is susceptible to liquefaction is. And that has to do with the distribution of the sand. So it may be that the sand is representing the old channel of where the river was, and within that area of sand, liquefaction could be a problem. When you get outside of it, it might not be. I've got some slides elsewhere that I would take me a while to find here, but there are places where liquefaction is over a broad enough area that it can cause quite a bit of damage to any buildings that are built on it. So as a general rule, it's better to avoid construction on areas that are susceptible to liquefaction than it is to build in areas that are. In the case, for example, of one of the more recent earthquakes in California, in San Francisco area, buildings that were built on hard bedrock they vibrated, there was damage, things fell off the wall, but the buildings didn't collapse. Whereas places where the buildings were built on landfill that had sand beneath it that was susceptible to liquefaction, there was quite a bit more damage. Some of the buildings collapsed, they fell off their foundations. There have been examples in Japan, for example, where whole apartment buildings that were 10 stories high just tipped over as a whole when the foundation gave way on liquefaction, on liquefied soil. And then, of course, if you're along the edge of an escarpment, if there's a bluff or some sort of cliff, liquefaction can cause landsliding. It can cause a large area of the bluff to cave out. That happened, for example, in the 1964 Alaskan earthquake, where often you may have seen huge amounts of damage associated with that earthquake. That's because Anchorage is built along the edge of the ocean, and there was a liquefying layer of sand beneath, and large areas of Anchorage slid out to sea on that liquefied area. So liquefaction is a dangerous hazard that has to be watched. Yeah?
Does a large number of small quakes along the St. Genevieve fault, for instance, almost unfelt, most of them, does that suggest that the fault is relieving itself often and maybe not have a large quake?
So the question is whether the occurrence of lots of small earthquakes is an indication that stresses are not going to ever be able to build up for a large earthquake. That's a possibility that people have thought about. Well, let me restate that. There is evidence in places along the San Andreas Fault where there's lots of small earthquakes happening that the stress does not seem to be building up to lead to a larger earthquake in the future. But you have to be careful with that idea because the difference in size between a small earthquake and a big earthquake is so different that it could be that the small earthquakes are inconsequential in terms of relieving the overall stress. And the reason I say that is that when you look at the difference in amount of ground shaking from a magnitude of say 4 to a magnitude of 5, the difference is a factor of 10. So magnitude 5 is 10 times as much ground shaking, and it's 32 times as much energy release. So when you go up a few orders of magnitude, you're dealing with millions of times more energy than there was on a smaller earthquake. In fact, one magnitude 9 earthquake, like one of those super earthquakes that happened in Japan or Sumatra, that single earthquake releases more energy than all the other earthquakes on the planet combined for the entire year. And so there's so much difference between them that it's, while it could be that small earthquakes are releasing some of the energy, it could also be that it's not enough to make a difference. Yeah.
Went to a presentation in Jefferson County, and there was a document delineating certain zones, and to fully communicate to the public, it had the section, range, township on the map. It also had roads. I think it was Platham Creek. In other words, for us, it was something that we could interpret. And I was wondering, is a similar document that has roads, sections available on this St. Genevieve's Fault?
Well, that would, your question is about the level of detail of work that's been done to represent exactly where the fault is. There are more detailed maps. For example, my student's map of the area shows, is done on a base that has township and range and so forth. Often the state geological surveys will be the agencies that will be compiling that. For example, our particular project, we're looking at sort of large-scale features like the boundary between the Ozarks and the Illinois Basin, and we're not mapping out individual faults in great detail in general. But there are structures like that, and my understanding is that the Missouri State Geological Survey has all of that data online and available for downloading, so that you can go to a particular area, download the map of that area, and get the data that you want.
I'm just saying it's hard to relate to some maps, but if you show the roads and sections, we can...
Right. And again, it depends on the scale that you're looking at. Yep. Yes?
Is liquefied sand the same as a sand boil?
Yes, yeah, sand volcano or sand boil, those are just different terms for the same thing. They refer to situations where liquefied sand is able to make it through a crack or a conduit to the surface and then spill out on the surface.
Yes, I've seen.
Yes?
Is there any data to show the effect of an earthquake on underground caves south of the piers?
Yeah, so the question is there evidence about how earthquakes can damage caves? Well, I don't know about specific caves in this area. I do know that there were some studies done in Illinois where they were able to find stalactites that had fallen off and using various techniques get a sense of the age of those stalactites and determine when they fell, and it seemed like some of them might have tumbled during particular earthquakes. But if there is a significant earthquake, flow stones in caves and dripstones in caves are fairly delicate features, and it could be that they could be caused to break and fall. And in some cases, it could be that a sinkhole could be triggered perhaps by a larger event. But in terms of detailed studies, I'm not familiar. Again, that might be something that state geological surveys have more data on. Next question. Okay, I'll turn it over.
everybody hear me? Can anybody hear me? Can you hear me now? Okay, sorry. My name is Larry Pierce. I'm with the Missouri Geological Survey out of Rolla, Missouri. Some of the mapping that you were just talking about, I'll kind of answer some of those questions. I'm going to kind of talk a little bit about the Geological Survey, some of our disaster planning, and some of our mapping efforts that are going on in the state right now. One of the things that we found, or you find in disasters, is that typically when you have a disaster, it requires a rapid decision, or that decisions be made in a rapid time frame. And you have to consider both the short-term effects and the long-term effects. Decision makers immediately following disasters, they have to try to figure out what's the best thing to do for their community at that point in time, but at the same time, you don't want to cause any long-term kind of issues. You know, the important thing is sometimes they lack the necessary science or scientific information that they need to make those decisions. So how can the scientific community assist? How does the Geological Survey assist? We help by trying to proactively map, proactively provide information and provide data that decision makers can use, county planners can use, fire departments, places like that, folks like that can use, urban and regional planners can use. These are both in the forms of maps, site evaluations. I'll talk a little bit about doing site evaluations for individual farms and stuff like that, and having contingency plans. When we start talking about landslides and stuff like that, you know, you've got can map out avenues to exit areas. That in turn gives the decision makers those tools that they need to help make those decisions and have a more responsive plan. So in 2012, the Missouri Department of Natural Resources, the Missouri Geological Survey, and the State Emergency Management Agency began to team up, and we started to produce a series of maps called Geologic Hazards of Missouri. We went through and we started on a 1 to 250,000 scale mapping and produced all of the areas that have potential for liquefaction. So these are areas where we have groundwater that's within a few feet of the upper surface. We have sand sediments that are at the surface or near the surface with that clay layer at the top that Dr. Marshall talked about. And we also looked at areas that were karst in nature. Somebody mentioned sinkholes and caves. So we looked at areas that had the potential that if you had an earthquake, you started shaking this, what were some of the areas that could potentially collapse due to having those that karst underneath there. We've also done some other types of mapping. I'll show examples of this, what we call debris management mapping. With debris management mapping, one of the first things that we found in Joplin, I'll get to that in just a minute, but one of the first things we found in Joplin is we had a lot of debris and we didn't know what to do with it. We're also in the midst of a project right now working with SEMA, creating what's called MILO. It's the Missouri Inventory of Landslide Occurrences. We're trying to do both current and historical mapping, where we're mapping the landslides that have occurred over the last few years, but we're trying to go back and map landslides that occurred during some of the larger earthquakes of 1811 and 1812. If we can get an idea on the scale and the magnitude of those landslides, then we can get an idea on what we could expect if we have another incident. I talked, this information is available to the public. It's in the form of shape files. SEMA has them. The Missouri Geological Survey has them. If you go to the Missouri Geological Survey's webpage, they have something called GeoStrat. Geological Science Technology. I can't remember the exact acronym. It's government, and there's a long list of acronyms. I apologize. It has all of these mapping products in a Google Earth platform. So you can download these mapping products in that platform. We also have hard copy maps and PDF maps as well. So in 2012, 2013, we began to do this mapping of the geologic hazards. We looked at the earthquakes, the liquefaction, landslides, sinkhole development. We also looked at flooding, looked at dam locations, the location of large dams across the state, where they were at, and stuff like that. What we tried to highlight was, again, the liquefaction potentials, landslide potential. With the landslide, we looked at slopes that were greater than 20% or greater than 12% that were underlain by an impermeable bedrock unit such as shale or clay or something like that that could potentially perch water and accelerate it. Sinkhole development, we looked at cave locations, sinkhole locations and stuff like that, mine subsidences, and dam locations. Originally this was done to assess the locations, the best locations to stage during a potential earthquake, or to stage state resources during an earthquake or after an earthquake. If we have to bring in National Guard, or we have to pull people out of, you have a large earthquake in southeast Missouri and you're pulling several hundred people out and trying to house them, where do you want to go? You don't want to put your staging area where you can expect to have potentially landslides or land subsidence, that type of stuff. So it's kind of pre-disaster mitigation. MoDOT has taken a lot of these maps and began to lay their highway maps on top of that so that they can get an idea of the potential for landslides or catastrophic collapse, sinkhole development, and where it is in relationship to their road. So this is an example. This is probably, let's see, St. Jen's right here, I believe. Right here, St. Genevieve. This is a little hard to see. It's a little bit pixelated up here, but this is a geologic hazards map for the St. Louis area. This is Region C, the SEMA region, and it shows the areas of yellow here are areas that are greater than 20% slope, so there's potential for landslides. And again, I apologize, it's hard to see. Let me back up. I have this in greater detail here. Here we go. Here is a kind of a blow up of the St. Louis area. We have these maps at 1 to 24,000. You can see the yellow there. Again, it's very pixelated, but there's areas along in here. There are blue hash marks which show the areas that are underlain by sinkholes and where you could expect to potentially have sinkhole development along in here. And there's, okay, here we go. Here you can see the blue slash lines here. These are areas of potential for sinkholes. This area out here in the Mississippi floodplain is areas that has potential or are susceptible to liquefaction. So we've kind of gone through and gave a general overview of where these potentials are. This is north, this is southern Jefferson County. Same thing for along the Missouri River, the whole St. Louis area. We've got, this is the Missouri River, St. Charles is up over here, Chesterfield's down over here. So again, you can see that the potential for landslides and stuff like that. We have these maps for the entire state. When you begin to get away from the boot hill, the potential for liquefaction goes down considerably. However, you do have, just based on steep slopes and stuff like that, there is always potential for landslides. And you have wet weather and stuff like that based on slope. So here's some example from the Chesterfield area. You can see the areas that are greater than 20% slope. You can see the area right up over in here where we have sinkholes or sinkhole development. The areas underlain by caves or sinkholes. And again, out in the floodplain down here, we have the potential for liquefaction. So this was mapping the hazards, and we tried to figure out how's the best way to come up with a practical application for that mapping. And we kind of took a lesson from Joplin. In 2011, when the tornado came through Joplin, the first thing that you do is you have first responders get in and they take care of life and limb. I mean, that's the most important thing. Make sure everybody is safe, that they have food, they have water, and they have what they need to survive. But it's kind of that second wave of people that are beginning to come in, of responders that are trying to figure out, what do we do with all this mess? You can't leave it in place. because it begins to rot debris. You've got to get it out of the way, while at the same time, you can't just dump it anywhere. Joplin happens to be in an area that's underlain by permeable bedrock, just like St. Genevieve, Perryville, those kind of areas. You can't just go fill up every little sinkhole with debris, because the first thing that happens is you've taken a short-term problem and you've created a 25-year problem because you have groundwater contamination. So what we began to do, we began to look at what would we do for debris removal. In the state of Missouri, debris has to be treated just like municipal waste. So it has to have a confining layer between the debris and the underground drinking water. So we began to do a series of what we call debris mapping, or debris management mapping. This allows people, regional planners, emergency planners, regional coordinators, city planners, to get an idea. If we have an emergency, how far are we going to have to take our debris? In the city of Joplin, the closest landfill that was able to accept debris was 34 miles. That's a one-way trip, 34 miles for one way, so you're talking quite a bit, 68 miles there just to take one load of trash to the landfill. So it was very costly to do that. So disasters often produce a large amount of trash. This is a photo debris. This is a photo from the 5.0 earthquake that occurred in Oklahoma. So you can kind of see the chimney that failed. This is a photo from Joplin. The amount of debris and trash that it created. Creates a lot of trash, leads to a lot of confusion by decision makers, and it's all within an accelerated time frame. Given long enough time, you can figure things out, but when you're trying to make these decisions through the course of a week or two, it can get pretty difficult. So we began the debris management mapping program. It's essentially what we call a fairway analysis. This is something that comes out of the oil field. It's the best way to think about a fairway analysis is to think about a red light, green light, yellow light. So red light is no, it doesn't meet the requirements, or it's environmentally sensitive. Green light is yes, it's you're able to put trash there, and yellow light is well, maybe, kind of that in between. And like I said earlier, that trash in Missouri has to meet the solid waste requirements, 10 CSR 80-2, which is for the solid waste management program with the Department of Health. So it has to have that confining layer protected underneath it, and you can't put it in karst. You can't just fill up sinkholes with it. You don't want this stuff collapsing down into these areas. So we took these 7 requirements. That there's other requirements for the solid waste management program, and we began to produce a series of maps. We produced these from essentially Jefferson County down. This is the Cape Girardeau area, and you can see here we've got, this is on the maps, this is a lot more red. Essentially, we've got those areas that are underlain by regional drinking water with no protection from the surface. There are a few little areas right here along Crowley's Ridge, Bent Hills, that do have some clay in the area. And there's a few clays along just in Cape Girardeau County out there there are some shale layers that are present there. So those are areas that are possible to potentially put a solid waste management area if we had to, if you have a large amount of debris. Expand this a little bit. Those faults that the previous speaker talked about are in red here. So but there are some areas in between there that do have the potential for a confining unit. This is for the Farmington area over here. St. Genevieve is going to be right over here. Right there, sorry. The St. Genevieve area. It too has some areas that are underlain by shale. It's really hard to see. Some of these areas, there's actually 2 different colors here. There's a yellow and an orange. We also mapped out areas that were underlain by igneous bedrock. Those are areas that have lower potential for groundwater contamination because of the types of bedrock that are there. And then for the boot hill as well. The one thing that you notice from all 3 of these maps, there's not a huge area of really environmentally good places to put debris or to manage this debris if there ever was something to produce a large amount of trash, earthquake or something like that. Right now we're in the midst of working on a project, like I mentioned, called MILO, which is Missouri Inventory of Landslide Occurrences. We're going around the state, we're working with highway departments, county managers, basically anybody that we can work with, get data from, and we're trying to get an inventory of these landslide features that have occurred across the state, whether it's related to rock falls and bluff failures or slumping, something like that due to highway construction and excessive rains and stuff like that. One of the things that we know, and during an earthquake, if you have these areas here where you see landslides occurring, if you come back, if you start shaking these areas, you can expect that similar responses after you start shaking it. So this is going to basically look for current and historical landslides. We're including data from academia. We have a PhD student from St. Louis University that we're working with who's using remote sensing data to map a lot of these types of features. And ultimately the goal is to get this database on GeoStrat as well, so that we will have those landslide features, and that is available to the public. It's free. It's on a Google Earth platform. If you've ever looked at Google Earth, that's essentially all you're doing is doing this, and you can turn on the different geologic features as well. So some other different types of mapping or of disaster planning that we've been working with. We're also a part of a group out of St. Louis, what's called the SLAHIMP, which is St. Louis Area Earthquake Hazard Mapping Program, and we have produced a series of maps for the St. Louis area that is looking at the potential for shaking. We have a seismologist out of the University of Memphis that is in the process of just finishing all of these models that has looked at the potential for shaking. At the same time, they're looking at the potential for liquefaction. Has areas with the highest potential for liquefaction. Like the previous speaker was saying, the areas that we're seeing the greatest potentials for liquefaction are these floodplains where we have soft sediment sands near the surface, and you have very shallow groundwater. Here's an example. This is used by the seismologists to produce liquefaction acceleration models. This is a probability of ground acceleration. You can see along the bluffs on the Illinois side and out in the Illinois side, the potential for that ground acceleration is much greater compared to the bedrock of kind of the Missouri side. There's several of these types of models in that report. The other thing that we're trying to do too is we're also trying to be proactive with animal mortality. One of the things that we see, not only several different disasters, ice storms, high heat events, and earthquakes, is there is potential for animal mortality. This is an example of a very hot 2-week spell we had in July. One thing that happens is when you start getting hot weather, you are overloading electrical circuits and transformers start blowing. With the modern way that we are beginning to do a lot of our farming, we control the environment for those animals. If we cannot control that and keep that environment in control, then you have issues such as this. So we're doing a lot of on-site evaluations prior to the farm being developed, so that if something happens, they know how to take care of these issues before they or when they happen. Again, excessive heat, ice storms. Ice storms are heavy snowstorms where you have large amounts of snow on top of barns. Some other disaster planning that's going on is we're currently in the process of mapping the depth of groundwater for the Boot Heel in what's called a NEHR project. We're looking at the depth of groundwater down there, trying to get an idea on the potential for liquefaction, trying to narrow those areas down even more. It's primarily all soft sediment, shallow groundwater, but we want to know a little bit more detail. Where can we expect to see that? And then also we have an earthquake response plan at the Missouri Geological Survey, whereby we produce we open a clearinghouse in the event of an earthquake and try to consolidate geologic information and get it to our decision makers. Thank you very much. That's just kind of a recap of the mapping efforts and the stuff that's going on at the Missouri Geological Survey and the information that is available to the public. If you have any questions, I'll be happy to answer them. I'll be around afterwards. I can get you locations on where you can find some of this information as well.
Test, okay. Well, good evening, I'm Steve Bessemer. I'm with the State Emergency Management Agency. I appreciate all of you coming out tonight. I'm going to do kind of the final leg here, so hopefully you can hang in for a few more minutes. I work out of Jefferson City with the earthquake program. I'm not a scientist by trade. I hope that you're seeing, though, the importance of having the information that we can get from people like Dr. Marshak and Boot, the scientists who bring us this information. I think what I kind of want to do then is to kind of keep this transition going and say, you know, what do we need to do with this information? You know, how do we process this? Are there some things that we can do, and I'm talking primarily about you as local residents, to take this information to go home with? So I'm going to talk a little bit about that. I kind of take this, I'm a non-scientist, so I probably in some ways dumb this down a little bit more than I should for the scientific people here, so I apologize to them. But I have to kind of take it and try to say, okay, from an emergency management perspective, and Felix would be the same way, you know, what do we need to be concerned with in our community? What do we need to be concerned with in the county, the state? What are the hazards, the potential hazards that we worry about? And then what are the steps that we can take? So let's talk a little bit about that. You've seen some of the maps already that show earthquakes happening in the Midwest. They happen just about every day. So the information I take from the scientists about the history of earthquakes is great. That adds to my knowledge base. But then I'm also looking to say, well, are they still going on now? You can go to a map through the U.S. Geological Survey. They partner with the University of Memphis, and there's a website, the Center for Earthquake Research and Information, if you want to look it up. And you can actually go and day-to-day see, you know, a map of where the earthquakes are happening. So this is one I just pulled from the other day, and hopefully you can see. Oops. You can see southeast Missouri that we have this conglomeration of earthquakes that have been occurring. You know, these are over the past 6 months. These earthquakes are happening. So we can see, you've already seen, we have a history of earthquakes that have gone on. You can see the earthquakes are still happening here in this part of the country. So me, from the emergency management perspective, then I have to kind of treat this as something that, hey, you know, is this something that we need to be prepared a little bit more for? You know, do we need to continue these type of coordinated mapping projects like Boot was talking about a moment ago? Obviously, first and foremost, in the somewhat recent history, these 1811, 1812 events that happened in the Mid seismic zone, you know, just thinking about the enormity of this situation, 3, probably 4 of the largest earthquakes to occur in what's now the United States, east of the Rocky Mountains, happened not far from here. And these are just the big ones. You know, there were numerous aftershocks happening, you know, hours apart, for days upon end, weeks upon end. Really over about a 5-month period, I think there was about 1 day where there was not a recorded earthquake during this time. So this is something just to kind of have in the back of the mind as well. It wasn't a situation where, hey, there was one big earthquake and then everything just kind of settled back in place. This was very unique in the fact that these people that were here, the few people that were here in this part of the country at that point in time, really had to endure with this. And, you know, certainly I'm not telling you anything new for those of you who were around in 1993 and 1995, when the waters were up and they didn't go down the next day. They were here for days and weeks upon end. Much the same way that we would have potentially with large-scale earthquakes happening again in this part of the country. Zoom in a little closer, we zoom into the St. Louis area. Because we tend to think New Madrid, sometimes people in around, when I go travel the state, go to the St. Louis area, go to mid-Missouri, southwest Missouri, whatever. You know, people think of New Madrid and think that's the only places where we really have these earthquakes happening, where we have even significant earthquakes happening. But from this information from the Earthquake Center at St. Louis University, you know, at least a dozen earthquakes have caused minor damage in St. Louis. So again, I'm not just worried from the emergency management side about the folks that are in Cape Girardeau and on down to Arkansas. I have to think a little bit wider area as far as the potential for damaging earthquakes and the problems it could cause. Even closer to home, 1917, Weingarten is considered to be the epicenter of this earthquake, about a 5-point magnitude earthquake. You know, it's certainly been felt. It was felt, minor damage, not far from here, and certainly right around in here as well. You know, is that something to get alarmed about? You know, with minor damage? I mean, is that something for us to panic about, to do large-scale planning and mass mobilization of people to get ready for something that causes minor damage? Because we don't know what the buildings were built like, what kind of shape they were in, what exactly was the minor damage. You know, there are a number of factors that go into that. I think it's just something to be aware of, to consider for whatever you do for your planning purposes or potential planning purposes in the event of future earthquakes happening here. The Mount Carmel earthquake in April of 2008 happened at about 4:37 in the morning, 5:37 in the morning.
Yep.
Mount Carmel, very near the Indiana border. Earthquake was about a 5.4 magnitude earthquake, so it wasn't huge compared to 1811, 1812 standards. The map here is from a USGS program called Did You Feel It? Where you actually, if you think you've experienced an earthquake, you can go online, you can fill out a report and say, yeah, I was, you know, at this time of the day I was doing this, and this is what happened, you know, the dishes fell over, and, you know, these other things happened. And then you hit send, and it goes in and it populates this map. And so if you can tell, it's the colors on there, there's different colors there. And the yellow part in the middle is the epicenter of the earthquake here. This is Evansville, Indiana. Here's St. Louis, Springfield, Illinois. This is back in mid-Missouri here. And all throughout here, there are little colored chunks where people reported feeling this earthquake. Anybody here remember that earthquake? Yeah. People here felt it. The State Emergency Management Agency, our on-call person, first call they got, I think, was from somebody, I think it was Herculaneum. It was up in Jefferson County. Somebody was in Herculaneum was reporting it to us. The second call was somebody from the fire department in St. Joseph, Missouri, all the way in the other part of the state. They felt it there. There's over 400 felt reports on this site from Kansas City. So this is another thing, and I think you may have probably gotten a little bit of this from the previous presentations, is you don't have to be right on the doorstep of this earthquake to feel the effects of it. And in many cases, really in this part of the country, we're going to feel earthquakes up over a much wider area, at least a 10 times wider area here than a similar size earthquake in a place like California. So that's another thing to think about. You don't have to be in New Madrid, Missouri, to have to be worried about possibly feeling an earthquake. And many of you have this personal experience already. I slept through it though, in Jefferson City. I woke up right after that. I didn't know why I woke up, but I woke up. And I thought, that's kind of weird. Then the phone started ringing, and then I knew why. All right, I've heard about this event. I look at the history again. 1811, 1812 was not an isolated event. We had these clusters of earthquakes in 1811, 1812, happening roughly in this part of the country, series of large earthquakes. Through the paleoseismology work that's been done, that you heard a little bit about earlier, they believe that there are other periods of large earthquakes have happened in this part of the country around 1450 AD, around 900 AD, even back before that, around 250 AD. So for me, I'm looking at it saying 1811, 1812 apparently was not just an isolated event. Why is this thing happening over and over? Why are we having these recurrence of these types of large earthquakes? So for me, that's like, we got to think about this and think that, hey, if it's happened these 3 or 4 or 5 times previous in history, should we expect it again? And it's something to at least investigate. It's something that may not ever happen in our lifetimes. We may never experience large earthquakes again. We may never feel an earthquake again. We may just have little ones around here and never have anything significant. But certainly the possibility is there. This is more or less just what the U.S. Geological Survey says. 7 to 10% chance of a large earthquake in the pneumatic seismic zone over that 50-year period that Dr. Barczyk was talking about. So it's not like it's going to happen, we start the clock and 50 years from now, this is the probability. It's in any 50-year span. So that's just a rough number that they use, but there's certainly a chance of moderate or even significant earthquakes occurring. And we need that because people always want to know. The emergency management people are probably some of the worst at bugging scientists saying, what's the odds? What's the odds of having an earthquake again? What's the odds of having a 100-year flood in this area again? We're asking those questions because we need to plan. We need to help our citizens plan and be ready in case these events do happen. The concerns that we have, earthquakes are low probability, high consequence events. We've never been through a damaging earthquake here in the Midwest in our lifetimes. The Great New Madrid earthquakes in 1811, 1812, there's nobody around here today that lived through those. So it's not something that happens near as much as floods or tornadoes or ice storms or power outages or some of this other stuff. So we don't need to hold an event and come here and tell you folks that, hey, you might have flooding here in this area. Or you might have some downed trees from windstorms. You've got that experience, you've got that knowledge about that. Earthquakes are a little bit different though, and it is difficult to go and talk to people and to put that on the top of your list preparing, and I'm not necessarily asking you to, but to remember that these things are possible. We don't have this working knowledge of large earthquakes in the Midwest. That's my words, working knowledge. And we consider a recurrence of the 1811, 1812 New Madrid events as our Katrina. We look at that as kind of our worst case scenario. Again, it may not happen in our lifetimes. We may not have these big earthquakes again anytime soon. But if we did, when you look at the implications of having that large area covered, we look at some very big potential problems with that. Depending on where the actual epicenter is of the earthquake, depending on the amount of aftershocks, the strength of the aftershocks. You have all sorts of concerns that can come in as a part of having these big earthquakes. I want to play a little video here real quick. I have to be kind of a visual type person, so this helps me by having videos like this. This is a testing that was done basically to what they call a shake table in a university setting. And I believe in Illinois they have shake tables as well. You build something in a large area, you build it, you can build it like a house, and in this one, this is one that kind of made the frame of a house several stories. Put furniture in it. Some of the stuff that's in there is attached. Some of the stuff is not. And then they move it back and forth on this large platform to recreate the shaking of an earthquake. So this is actually based off an earthquake from Japan. And you're going to see the same movement's going to happen over and over. We're kind of giving you the wide view here, and then we're going to go and they're going to play it over and over by cameras, which are in each of these rooms. And those will be a little bit clearer as we get to the closer shots. This is about a 7.0 magnitude earthquake that's going on here that they're recreating. Shaking from some of the larger earthquakes in recent years have been reported to be felt for several minutes. So think about having that experience of having that kind of movement going on for several minutes before it really gets steady. But it can also be a very short time, 30, 45 seconds as well. So they're moving it back and forth. Now we're going to zoom in and start looking at the room. And that's where I get more concerned, because I want to see what's going on inside these rooms. What's happening to the stuff inside of there? What's happening to the people inside of there? This is an office setting, some bookshelves along the far wall, desk, copy machine down here. Now the earthquake starts. Copy machine is not tethered, not secured. Bookcases are not bolted to walls. And so if nothing else, even if nobody is in this room, you as a business owner or school administrator or whatever, you got some things to clean up, and you've got some things that are probably damaged. And I'll show you a few more sequence of this as we go through. None of this stuff was secured for the testing in this particular room. So you've got all this damage going on down here that you have to clean up, if you can. Got laptops on the desk here. Got a copy machine still on its wheels. Laptops have been tethered into place. Kind of a little cheap little, inexpensive way of securing things. Often can help you have to not worry so much about replacing everything. Person working at a table there. Everything's going to move again, office setting. I like what the dummy does in this particular situation. Gets down on the ground, gets under the table. This is why you don't want to think about, if you're ever in an earthquake or a big earthquake, you don't want to try to run for the door, try to get outside, or try to get inside. If the shaking is that intense, you're not going to have that time. You're not even maybe be able to move that much. It's going to be very difficult to do. I'll show you a couple more and then we'll move on. TV goes over. Again, stuff that is high, bookcases, file cabinets, stuff like that, might not perform so well when earthquakes occur. Last one here. Somebody's taking a nap. We've got dressers and things in the background. We'll see if they're secure or not. Yeah, it doesn't look like it. Now that person there has now become a victim or somebody we at least have to try to figure out how to get some help for. So these are the things we show in order to talk about what's actually going to happen. Get some idea of what's going to happen to somebody during an earthquake type of event. At the state level, we've done planning for earthquakes really since the early 90s. Any of you remember Ivan Browning? Okay? 1990, December 1990, Ivan Browning, a climatologist, I believe, from New Mexico, said that all the planets are going to line up, be in perfect alignment, will create enough of a gravitational pull that to create an earthquake on the demanding seismic center. I was in this area too at the time it happened. And I think the rumor just kind of hung around long enough and people didn't really take it seriously at first. And then it was kind of like, well, maybe this would happen. And then I think like in September or October, there was about a 4.6 magnitude earthquake near Cape Girardeau. And then all of a sudden it's like, oh my goodness. And so, schools were closed. There were people going around doing presentations about earthquakes and earthquake preparedness. People were filling up buckets and trash cans of supplies that they called earthquake kits and kept those around. And, and then, of course, when that day came, there were more media than people in New Madrid, which was a really bad place for the media to be if the earthquake happened, but nevertheless. An earthquake happened and you could almost feel people going back home, dumping their kits out and putting everything back up on the shelves. More on that later. But we do planning since the early 90s. The response is basically going to be that we're going to have a coordinated response, local, state, federal level, if a big earthquake does happen. We try to plan for the worst, hope for something not as bad. But obviously seeing that Missouri would not be the only state affected, potentially by a large earthquake in this part of the country, you could have up to 8 states pretty heavily affected. Those states would need help from neighboring states, and then pretty soon you have a pretty significant national type of emergency. So this process we've been working through, and part of the mapping that Buddha's been talking about is help us identify potential hazards. Because, hey, it doesn't do us any good to plan to come down Interstate 55 with a whole bunch of stuff to come help people in Cape Girardeau and Kennett and Sykeston if there's potentially a problem with landslides or something like that on that highway. So that's why whatever information we can get to help this planning process go smoothly, we want to find out that info now. So you'd have about 7 million people at high risk. Again, like most of these things that we give you, that the USGS gives you, that FEMA gives you on these things, we're trying to be cautiously, the numbers may seem a little high, maybe, but we're trying not to think the worst case, absolute worst case scenario, and then try to plan to meet those demands as best we can. You have such a large area potentially affected by this. One of the estimated impacts that was done a few years ago for some of the work talked about maybe up to 3,500 fatalities in these 8 states, 715,000 buildings damaged, all sorts of stuff. Debris generated, we're talking about debris, 50 million tons of debris. Where does that go? So you have potential problems that certainly would make this, you know what the situation was here after the flood in '93, how long it took for the levee to get built, to things to kind of get back to normal. We're talking about something that would be much more much longer period to kind of get back to normal over a much wider area. Just because it's going to take a long time to get around to start fixing everything up if you have such a wide area affected. So again, we have to look at these numbers. We're not saying these are the absolute, facts that will happen if there's a certain earthquake of that size happening, but we have to try to get our arms around it and start planning as best we can. There are things you can do now before an earthquake to prepare. That planning process is part of it on the state level. For us on the emergency management side and the governmental side. But there are things people can do as well. When flooding occurs, oftentimes you know days or even weeks ahead of time of potential flooding conditions here. With tornadoes, you may know hours ahead of time. You may have watches out that turn into warnings, and then the tornado does come through. With earthquakes, you don't get any warning. There are earthquake warning systems being developed, I think originally out of Japan, which are now coming onto the West Coast, and they're developing an earthquake warning program, and you can get a notification saying that an earthquake has happened, and you might get 30 seconds, 45 seconds, a minute, to do something before those waves get to you, depending on where you're at. How much can you do in that time? You can do some things. You can maybe move to a safer place. If you're a fireman, you can maybe get the doors open on the firehouse. You can get the trucks out. But there's not a lot you can do in that amount of time. So doing things now to prepare, I would encourage you to do. Learning about earthquakes. We're doing that here tonight. Developing family plans, emergency communications plans, checking for hazards in the home, school, church, office, wherever. Do you have the big bookcases that are in a bad spot that are kind of wobbly already and could tip over? Do you have maybe an old chimney right near your front door of your house or something, and hey, if it just gets a little shake, the bricks might all come tumbling down. Identifying those things now. Check for hazards outside the home. Know where your gas lines are at. Know where your potential hazards are at. So in case you have to leave your house in the middle of the night or in bad weather, it doesn't even have to be for an earthquake. Knowing the potential areas that you need to stay away from, or if you smell gas and you have to go shut off the gas, know how to get to them and access that stuff and have the tools there to do it. If you make a plan, make sure everybody in your house or your business knows about it. There's nothing worse than having somebody who's the all keeper of knowledge in your house or your office, and they don't want to tell anybody where everything is at. There's a certain advantage to that, I guess, but if that person is the one who knows where the emergency supplies are or where the extra key is to get in and out of this area, that doesn't do you any good. And of course, considering special needs, whether it be people, whether it be pets. And again, start thinking about, even if you listen to all this stuff tonight and think, never going to happen. Never going to happen. Never going to be an earthquake. Never going to happen. Think about the other situations you might be in. Think about ice storm. Power goes out for days. People not that far away from here down in the Boot Hill, a few years ago, there were people that were out without power for 3 weeks. What are you going to do if you're in that situation? That's a long time to be able to sustain yourself. And if there's a bunch of other people out there, you may not have enough shelter areas to get into. You might have your local officials might be overwhelmed to help each and every person or get to each and every person. If you got heavy objects up high, put them down low. Don't put your bowling ball up on the top shelf of your bookcase. It does not work good. Move it down low. Strap your water heaters, cabinets, tall items to walls. You know, the water heater thing it's a weekend project. If you've never strapped your water heater to a wall, you can go to one of the big box stores. You can probably get something that's already ready to go, bring it home. It's a kit. You strap it, you secure it, and then if there is an earthquake, that thing doesn't fall over. If you don't do it and that thing falls over, number one, potentially you have a gas leak. If that tank pulls over, pulls the line loose. And then number two, you potentially lose a source of water that you might need if other water is not available. Some good potable water. So, and again, it doesn't take much money. It's cheap. You can do it. It's, you know, it's a weekend project. You can do that. Brace light fixtures, overhead light fixtures, fluorescent light fixtures that you see. You know, those things, it's a matter of just having a couple wires, diagonal corners, and making sure they're secure up top to help brace them from swinging back and forth. A few years ago out in Virginia, the Louisa School District lost a couple of school buildings from an earthquake that happened out there. And there's a video, a security video, of some of those light fixtures coming down in a, thank goodness, empty hallway. But those things come down, they will hurt people. They could kill you. And again, the fix is easy. Safety film on windows, put together home office preparedness kit. If you still got your old earthquake kit from 25 years ago, or whatever it was, great. Just make sure you restock it. Change the stuff out. If you don't have one, you know, get one. Get some extra water in there. Get a blanket in there. Get a first aid kit in there. Get a flashlight with some extra batteries in there. Get a radio so that you can either crank it up or put batteries in it and listen possibly for information. There's also a program called Ready in 3, which the state of Missouri has. The Department of Health and Senior Services has worked with that. It's probably available through your local health department here, more information about it, or even some of the actual handout, written information for it. You know, basically what to do to help you be better prepared for emergencies. 3 steps: create a plan, prepare a kit, and listen for information. So Ready in 3, there's a number of sources out there. You know, FEMA, our federal partners, on our SEMA website, there's stuff about, you know, preparing kits and doing all the stuff ahead of time. Ready in 3 program has some easy steps for you as well. So there are a number of things, a number of different programs, types of things you can look at if you're interested in doing a preparedness like this. Map Your Neighborhood program is something that our State Seismic Safety Commission has supported. It's a program which comes out of Washington State. And we've kind of made some efforts to get it into Missouri. Hasn't really taken root yet. But it's kind of a cross between Neighborhood Watch and community emergency response teams, or CERT programs. It's basically just if you've got a subdivision, a neighborhood with 10 or 12 houses, and you all get along reasonably, and you kind of like to look out after each other, there's a formal program that can help you do that. It's called the Map Your Neighborhood program. Why would you do that? Because an emergency happens, the first responders are out. If you can be there as a neighborhood, or even as a household or whatever, the more prepared you are, the better that you are to withstand whatever situation it is, that responder can go on down the street and help somebody else out. Because, after the big earthquake, there's going to be a lot to do. After a large tornado or something like that, after the Joplin tornado, there was no ability for first responders to get out and get to everybody like right away. So you need some time, at least that first hour or so, where you can be as self-sufficient as possible. And certainly, if it's something where you're isolated, we used to tell people, be prepared to be on your own for 72 hours. And really, that's lengthened out some. Even in our state plan, working with FEMA, our federal partners, they pretty much have gone to longer than 96 hours to be on your own, 4 days on your own. Can you be on your own for 4 days without getting any help? That's the reality of the situation. That's not ideally the way we would want to do it, but the more that people can prepare to sustain themselves, certainly we would encourage that and try to give whatever means we can to help them do that. During an earthquake, you don't have a lot of time necessarily, so there's not a whole lot of steps here on this one, so hopefully you do most of it before. But we want you to drop, cover, hold on, 3 steps. We do it that way because it's easy for kids to remember, number one, but you're not going to have a lot of time. You have to take simple actions, and you have to do them rather quickly. Pictured here are some students down in Kennett, Missouri. There's some kids who are outside on the playground and demonstrating the drill. And it shows you that you're not going to go off running in all sorts of directions. You're not going to form a single file and all walk into the school building and find a safer place. You're going to take that action right away. And you're going to take it in hopefully as open an area as you can find in a short amount of time. Drop to the ground, take cover if you can, and hold on until the shaking stops. We really push drop, cover, and hold on. Because again, you don't get any warning. We want people to know what to do, especially these kids, and to practice that like they do other drills. Drop, cover, and hold on. If you're inside, stay inside. If you're outside, stay outside. Unreinforced masonry buildings or brick buildings, old brick buildings, anything that's probably over 50 years old probably doesn't have any sort of reinforcing steel or anything in it. So they're very vulnerable when the ground moves back and forth like that. You know, it's like you could stack Lincoln logs or dominoes. Hey, it looks pretty solid. Okay, now shove the table back and forth, see how long they stand. It's the same thing with those types of buildings. And so you don't want people trying to go in one of those buildings or out one of those buildings or in a building that has a chimney by it or an overhead ramp or lights that could come down. They're just dangerous parts, entryways to buildings a lot of times. So stay where you're at, take cover, hold on to whatever cover you have, table, desk, hold on until the shaking stops. Most people are injured in earthquakes from things falling on them, not from the building collapsing on them. So we're not worried about the ceiling just pancaking down on top of us if an earthquake would happen right now here in this building. I would be more concerned, I'm not saying there's anything wrong with this building, but just as an example, I'd be more concerned about the lights above, if there's projectors above, you know, what other stuff is above here that could potentially come loose and fall down. And you saw some examples of that in that video a moment ago. The Napa earthquake, the 6.0 earthquake that happened in California a few months ago, the wine earthquake, that was almost a tragedy because of all the wine they thought was damaged. Dr. Marshak talked about how a lot of buildings fared very well. California has a stricter building code. They have a building code. They make people build newer buildings to a higher standard to withstand earthquakes because they have more. Buildings fared fairly well. There was damage inside with some of those other elements inside the building. There was one death, and it was a lady whose TV set fell on her, hit her in the head. So it wasn't the building caved in on her or something like that. It was the stuff inside it. And again, when you look at that video and you saw all the equipment moving around and falling, that's where you as a business owner would have to be shelling out some bucks potentially to get back going again because of the stuff inside, not because your building came down. Don't get in the doorway. Doesn't protect you from falling items. Again, particularly if it's an exterior doorway where stuff could be peeling off or coming over the front wall. Also, for kids, we don't want them standing in doorways because doorways usually have doors on them. Doors tend to swing back and forth. They might get hit by the door. They might get their fingers crushed in the door jamb or something like that as well. The other important thing is that if you've got 30 people in a room and there's only one door, how many people are actually going to fit in the doorway? If I get there first, it's 1, because I take up a little space. So that's not a good situation to be in. We do have our shakeout drill. It's basically just like we do tornado drills, fire drills. We do one every year. It'll be October 15th of this year at 10:15 in the morning. It's a chance for you to publicly participate by actually going to a website and signing up as an individual, as a school, as an organization, as a business, and saying, yeah, we're going to participate in this earthquake drill. The drill takes 1 minute. You can do more, you can practice more if you want, but we're just asking you to get down and do drop, cover, and hold for 1 minute at a minimum. We had 3 million people in 10 states participate last year in it. In the central U.S., we've kind of latched on with other parts of the country, and it really has become a national earthquake drill. California does theirs at the same time. So we have millions and millions of people all across the country do the drill at the same time. If October 15th is a bad day, if 10:15 is a bad time, do it at a different time. But just sign up and participate and show you're participating in it. The 2 school districts in the immediate area here participated in the earthquake drill. Thank you very much. And so we know that they're taking part in that. School districts who are in the 47 counties, basically the 47 easternmost counties in Missouri, by statute are supposed to do 2 earthquake drills a year. And that's because they are in counties which, if there was a 7.6 magnitude earthquake happening in the Manhattan seismic zone, these 47 counties have been deemed to be the areas where structural damage could occur. And so they're considered to be the most at-risk counties in the state. So almost half the state really is in this. So you can register now, Shakeout. So it says it's shakeout.org/centralus. You go to the website, you can sign up. You don't have to be listed on there if you don't want to, but you can if you want, you can be listed on there. There is my contact information. I do want to thank you for your attendance here tonight. Before Felix comes back up, I want to thank Dr. Marshak for traveling all the way from the beautiful Champaign-Urbana campus, I believe, University of Illinois. I hope you found his information interesting as well, and to Ruth Pierce as well. We work together a lot, which I think is a good thing, because if you think you're ever in an earthquake, and you want to find out if you're in an earthquake, you can fill out that report. You might be able to contact your local authorities or officials, your emergency management person. I get calls in Jefferson City sometimes from people wondering about that. If it's scientific related information, then I work with Boot to do that. But if it's something but if he gets a call and somebody wants to know how to do an earthquake drill, then he refers it to me. So we think that works good, and it helps us all to prepare better. There's information out there on the table, books and handouts, and there's some maps that are kind of rolled up that I didn't get unfurled all the way, and I apologize. But feel free to take those. The U.S. Geological Survey publications, if we run out, we can probably get you some more of that, and I can even bring stuff down and leave it here or something like that if you're interested in having more information like that available. So I will wrap it up, and thank you very much. Oh, here's an example of the kit too, Red Cross. So if you want to come up and look at that and see what's in there, feel free to.
If you have any other questions, we'll be around for a while, putting everything up. So contact on the DPS side, and definitely you can get a lot of information off that. That link to any, if you get the DPS side, you can get linked to any state site too. There are links on the bottom of that to everything else in the state. So any other questions on that? Just stop and talk to us afterwards. Thank you.
Thank you.